of 101 slides, so we'll cover half of the slides today and half of these slides then in tomorrow's lecture. Till now we discussed the elastic analysis where we go up to the Fy, that is up to the elastic stress, elastic limit, and then plastic, the strain hardening, the stress strain curve for the mild steel. Already you discussed that in the previous semesters. So today we will be making an application of those limits, and it will be a kind of revision also. Most of this stuff will be again popping up and it will be kind of revision. So let me go to the presentation mode, and we start with the second slide now. Topics to be covered in this module: introduction, plastic hinge, then we have yield movement, plastic movement, and shape factor. Shape factor, actually it's the ratio of the plastic movement to the yield movement. We'll discuss this in a moment. Plastic neutral axis and plastic modulus. Already elastic modulus we discussed. What was the elastic modulus? It was moment of inertia divided by C. I divided by C. C was the distance from the neutral axis. So this was the ratio of the moment of inertia to the distance from the neutral axis to the outermost fiber. Example 1 and 2, we will discuss how we find out these and how we relate these plastic modulus, elastic modulus, and on these things. Fundamental conditions for plastic analysis, collapse mechanism, method of plastic analysis, and then examples 3, 4, 5, 6, and 7 relevant to the plastic analysis. Now, continuing with this introduction, the plastic method of structural analysis is concerned with determining the maximum loads that a structure can sustain before collapse. So this is the determination of the maximum load which a structure can carry, and if you increase a little bit load beyond this, so what will happen? The structure is going to collapse. So this is the maximum load which the structure can carry. The collapse load is also known as failure load, the ultimate load, or the limit load. So 4 now names given to this one: collapse load, failure load, ultimate load, or the limit load given to the same thing. This is that maximum load which a structure can sustain. Now, so far our analysis of the behavior of structures has assumed that whether the structure are statically determinate or indeterminate, the loads on them cause stresses which lie within the elastic limit. Now, within the elastic limit, the stress was, now today we will go to the plastic limit also. Still it is having the provision to go and take more load. Design based on this elastic behavior ensures that the greatest stress in structure does not exceed the yield stress divided by an appropriate factor of safety. Fy, the yield stress, it is usually denoted by the Fy. So what we do in the elastic design, what we do is yield stress, we provide some factor of safety in terms of reducing it. That is, let's say Fy divided by 2. So 50% of the yield stress we utilize. And this way we incorporate safety in the design. So that was the concept of the elastic design. But now in the plastic design, what we will do, so we are going to discuss now, this is an alternate approach. Now, an alternate approach is based on plastic analysis in which the loads are required to cause the structure to collapse are calculated. Now, we want to find out actually in elastic structure what happens if you put the design load there. It is not going to fail. It is having almost now double capacity. If you put more load, then it is going and then it is failing now. So what is happening now to the structure? The structure is becoming safe, but meanwhile it is becoming uneconomical also. So now this alternate approach, what is now the base for this alternate approach, which is the plastic analysis? Here we want to find out the maximum load which will cause the structure to collapse. The reasoning behind this method is that in most steel structures, particularly redundant ones, the load required to cause the structure to collapse are somewhat larger than the ones which cause yielding. So the collapse loading are going to be more than the yielding, and we will prove this in a while. So design based on this method calculates the loading required to cause complete collapse and then ensures that this load is greater than the applied loading. Generally, plastic and our ultimate load design results in more economical structures. So already we talked about this one. We exhaust the full capacity of the material in this plastic design. The plastic method is applicable to structures constructed with an ideal elastoplastic material such as mild steel. So in case of the steel, you can use this concept, this plastic method of analysis. For brittle material, you cannot, because there we don't have well-defined plastic limit. If a piece of mild steel is subjected to a tensile force, it will begin to elongate. Do you agree with this? Stress is directly proportional to strain. The force will be directly proportional to the displacement or the elongation. If tensile force is increased at a constant rate, the amount of elongation will increase constantly within certain limits. In other words, elongation will double if the stress is doubled. So when the stress goes from 6,000 to 12,000 psi, they are directly proportional to each other. Now, when the tensile stress reaches a value roughly equal to 1/2 of the ultimate tensile strength, now ultimate is, instead of yield strength, we are talking about the ultimate tensile strength now. The elongation will begin to increase at a greater rate without a corresponding increase in the stress. In the first range, if you remember that straight inclined portion in the stress strain curve, how was the stress strain curve? The stresses were along the y-axis and the strains were along the x-axis. And if we draw a curve, so initial part we see an inclined straight line. So that is the elastic portion. There we have stress directly proportional to strain. But then a stage reaches where stress is not directly proportional to strain. At some point, even the elongation is going on at constant stress. Stress is not increasing, but elongation is going on. So the largest stress for which Hooke's law applies are the highest point on the straight line portion of the stress strain diagram is the proportional limit. So that peak point where the highest point where the stress strain line portion we have, that highest point, that is known as the proportional limit. And after that, this Hooke's law is not applicable. The largest stress that a material can withstand without being permanently deformed is called the elastic limit. So elasticity means it is the property of the material due to which it springs back to its original position after removal of the loads. And after this proportional limit, what happens? We have permanent deformation, which is plastic. Now the behavior is going to be plastic. Even if you remove the load, it is not going to come back to its original position. This value is seldom actually measured, and for most engineering materials, including structural steel, it is synonymous with the proportional limit. So elastic limit, proportional limit is kind of the same thing. For this reason, the term proportional elastic limit is sometimes used. So sometimes this elastic limit or this proportional limit, it is also known as the proportional elastic limit. The stress at which there is a decided increase in the elongation or strain without a corresponding increase in stress is said to be yield point. So yield point where the stress and strain are not directly proportional to each other. Strain is increasing, elongation is increasing without proportional increase in the stress or load. So that point is known as the yield point. It is the first point on the stress strain diagram where a tangent to the curve is horizontal. So if you see that small portion where tangent is becoming horizontal, that is actually this yield point. Now, the strain that occurs before the yield point is referred to as elastic strain. Before, it is elastic strain before the yield point, and after the yield point, now the strain produced that is known as the plastic strain, that is going to be permanent. The strain that occurs after the yield point with no increase in stress is referred to as the plastic strain. Now, the plastic strain usually varies from 10 to 15 times the elastic strain. We'll see this now from the diagram. It is 10 to 15 times the elastic strain, this plastic strain. Yielding of steel without stress increase may be thought to be a severe disadvantage. Now, you can say that the stress now, they are no more proportional to each other. At constant stress, we are getting now more strain. And it's a kind of disadvantage, but no, it's a blessing now. And how it is a blessing? When it is reaching to the yield stress, the material, it will give you more elongation. More elongation means more deformation. So it will be giving you a kind of warning that you make some arrangement now in order to prevent the structure from failure. What can be the arrangement now? Let's say you can reduce the load. You can put in some additional supports, such kind of arrangements you can make because of this excessive deflection, which is giving you a kind of warning. Another thing is in statically indeterminate structure, it is giving you a chance of redistribution of loads also. So here now, whatever I said now, it is written here, but actually it is a very useful characteristic. It has often performed the wonderful service of preventing failure because of giving the warning now due to omissions or mistakes on the designer part. So sometimes under design structures, but still because of the reserve strength, because of this redistribution properties of the materials, because of the warning, what happens now, it gives you plenty of warning, and this way you can prevent the failure of the structure. If the stress at one point in a ductile steel structure reach the yield point, the part of the structure will yield locally. Now you need to bring in now the bending stress distribution along the cross section of an element. How the bending stress, if it is within the elastic limit, how the bending stress is distributed, it is a triangular distribution. At the neutral axis, the bending stress is equal to 0, but at the outermost, it is going to be the maximum. So in elastic now, stress design, the outermost stress now, we say it has reached to the Fy, which is the yield stress. So that way it is becoming a triangular distribution. On the top, let's say it's a simply supported beams. We take a cross section at the midspan where the bending moment is going to be maximum. So what happens there, if we take a cross section, we draw a neutral axis. From the neutral axis along the cross section, we make a triangle now on the compression side, and we make a triangle on the tension side. The triangular, why triangular distribution? Because why neutral axis? Why this is called the neutral axis? Usually this is a very common question now in the interviews. Now you define me the neutral axis. So most of the time, the students or the candidates are saying it is that very axis where the stresses are 0. No, where the bending stresses are 0. That is the appropriate, because then the interviewer, he is asking, okay, now you tell me what about the shear stresses. So shear stress is going to be maximum at the neutral axis, where the bending stress is 0. So in all, now the summary is, in elastic analysis, the bending stress distribution along the cross section is triangular. minimum at the neutral axis and maximum at the outermost surfaces. So if the stress at one point in a ductile material structure reaches the yield point, now where at the outermost it is going to reach at the yield point, that part of the structure will yield locally. So that part, the outermost structure now it is not going to take any further stress now. It has reached the Fy, and after this what will happen? It will stay at that Fy, but the lower fibers or the lower now layers will start now immediately attached to it. It will start yielding now. And it will go on until it reaches the neutral axis. And a point will reach where all the cross section will be under the yield stress. And that when that situation happens, we say that now this is the situation where the plastic hinge has formed. And if you increase load further, what will happen? It will now it will not be able to take any further movement now, because we have exhausted the full capacity. So without stress increase, thus preventing premature failure. Why premature failure? If all the cross section is getting to the Fy all together, and if you increase the load further, it will give you a failure, a fail structure. But what happens first the outermost fiber is getting at the yield point, and that is now yielding locally, followed by the attached layers now that starts yielding further, and that way it is now carrying more load. Now it is having the capacity to carry more load. This ductility allows the stresses in a steel structure to be readjusted. So because of this ductility, what happens? Yielding of the outermost layers will start, followed by yielding of the attached layers which are towards the neutral axis. So this will allow the more deformation, and because of more deformation, what will happen? The stresses in the steel structure will be readjusted. In other words, very high stresses caused by fabrications, erections, or loading will tend to equalize themselves. So the structure is not going to fail because of the excessive loading. What will happen? It will start redistribution. At one point, if it is getting overstressed, it will start redistribution of the stresses. It can be said that a steel structure has a reserve of plastic strain that enables it to resist overloads and sudden shocks. So it is all because of this redistribution of the stresses. So it has reserved plastic strains. After the plastic strains, there is a range now. From elastic, we went to the plastic now, and from the plastic, we are now getting to another one which is known as strain hardening. Plastic limit was inclined starting from the origin going up to the proportional limit. Then it became horizontal, and that horizontal line of the stress strain curve, that was the plastic limit. And after that, this now it can take more stress now. So again, an inclined line you will see, and that is known as the strain hardening. But engineers don't consider that, although it is giving you more now strength, more loading capacity of the structure, but it is not considered in the design, and that is considered as negligible. So after the plastic strain, there is a range where additional stress is necessary to produce additional strain, and this is called strain hardening. Now, this portion of the diagram, strain hardening we are talking about, is not too important to today's designer. A familiar stress strain diagram for mild steels is shown in the next slide. So you will see it now, and it will be kind of now a refresher to your minds. So you will, whatever you studied in the previous semesters. Only the initial part of the curve is shown because of the grade deformation that occurs before failure. At failure in the mild steels, the total strains are from 15 to 20 times the elastic strains. So this is again the plastic strain. It is 15 to 20 times the elastic strain. And here now we have that stress strain curve now. Here you see strain is along the x-axis, stress is along the y-axis. How the stress is calculated, you will have to now recall the testing which you performed on the universal testing machine, UTM. How the bar is now put in the two jars and how the stretching is applied, the load rating and all these things. So you have the cross-sectional area of the bar, you have the applied load from the dial gauge. So load divided by this A, it is equal to F now, which is the stress, and strain elongation divided by the original length. So that gives you the strain. So at different intervals, you draw the stress versus the strain now, join those points, and this diagram we get. Now this initial state point originating from this origin and up to here, this is now that elastic limit. This is the elastic yielding or elastic range here. Now here, after proportional limit, we have two kinds of behavior of now. This dashed line, it is known as upper yield, and the lower, it is this solid line, this portion is known as lower yield. Upper yield, if the rating load, this loading rate is fast, so then we have this dashed line, this behavior. And if it is slow, gradually if the load is applied, so then we have this solid line, this behavior, upper yield and lower yield. And this horizontal straight line, if you see here, this stress is constant now, but we have strain, it is increasing up to here. And after this now, again, more stress is required to produce further elongation. You see here now, again, it is rising now. So this is known as plastic yielding or plastic range. This range is horizontal, is plastic range. And after this plastic range now, strain hardening is, so this portion is ignored in case of the design. So this is the stress strain curve where all these three ranges are shown. Elastic range, and then the strain hardening. And now for simplicity, what we will do, we will use this as a straight horizontal line here, this portion. We'll assume the load is applied gradually. Now the curve will actually continue up to its maximum stress value and then tail off before failure. A sharp reduction in the cross section of the member takes place called necking. So if you remember necking, and after necking what happens? Necking, it is the reduction of the area actually, the sharp reduction of the area, and after that then failure happens. So that necking is followed by the failure. This stress strain curve is of usual ductile structural steel and is assumed to be same for members in tension or compression. Now somebody can ask you that the steel material you used in tension, why didn't you use it in compression? So in compression we don't use it because then buckling is coming. And because of the buckling we have the lateral instability. So in tension we don't have the buckling problem. So that is why in machine it is used in tension. The shape of this diagram varies with the speed of loading, the type of steel, and the temperature. So stress strain diagram, this shape will change and it will depend on the speed of loading, the type of steel, and the type of steel means grade 40, grade 60, like those ones. One such variation is shown in the figure by the dotted line marked upper yield. So this is one such variation. Upper yield and lower yield, if you want to see it again, so this variation is here, upper yield and lower yield. It is for the same material, this stress strain curve, but it depends on the loading now. For Now, faster loading, we have upper yield, and for the gradually applied load, we have the lower yield. Now, this shape stress strain curve is the result when a mild steel has the load applied rapidly, whereas the lower yield is the case for slow loading. So, rapid loading is causing upper yield, and slower load is causing lower yield. Plastic theory was introduced by J.A. Van den Broek in 1939, which is called limit design. So limit design is based on the plastic theory, which was introduced by this Mr. J.A. Van den Broek in 1939. Now, for the purpose of plastic analysis, we shall neglect the upper and lower yield points and idealize the stress strain curve as in figure on the next slide. We shall also neglect the effect that the effects of the strain hardening, but since this provides an increase in strength of the steel, it is on the safe side so to do so. Strain hardening, it is giving you an extra capacity now, but in design we don't take it, and if you ignore it, it is giving you even more safety now. These are the three assumptions we are making. Finally, we shall assume that both Young's modulus and yield stress have the same values in tension and compression. So E and Fy will be same in tension as well as in compression in this plastic analysis. First introduction, idealization of the stress strain curve. Second was ignoring the strain hardening portion. And third is the Young modulus and yield stress is same in tension as well as in compression. Here, this is that idealization, this plastic range, and it was said that it is 15 to 20 times. So here you see if this is 1, so it is almost 15 times, or let's say 20 times of this elastic range. This is the plastic range, and here it is made straight now horizontal. That upper limit and lower limit that has gone now. This is the idealization, and it is same. Let's say it is in tension, so it is same in compression also. Tension and compression, the behavior is the same. Now, the basic theory is that the stress distribution changes before the stresses at certain point in a structure yields the yield point. The basic theory is that the stress distribution changes after the stresses at certain point in a structure reach the yield point. Redistribution will happen, and this is the basic principle. Those part of the structure that have been stressed to the yield point cannot resist additional stresses. Up to Fy at a particular layer we go, and after that what happens if we further increase the load, that stress in that layer is going to remain the same. But next to it, the layers will start reaching to the Fy, to the yield point. That is the idea, and we will now show it in diagrams also. These parts will yield the amount required to permit the load or stresses to be transferred to other parts of the structure. So this is about the redistribution. The stress strain diagram is assumed to have the idealized shape. Okay, we discussed this already. The yield point and the proportional limit are assumed to occur at the same point for this steel, and the stress strain diagram is assumed to be perfectly straight line in the plastic range. Beyond the plastic range, there is the range of strain hardening. So elastic range, plastic range, and then we have the strain hardening. And here on again, this is elasticity. In this portion, the elasticity is applicable. Then this straight horizontal portion, plasticity, and this is the strain hardening. Again, idealized stress strain diagram. This is the here along the y-axis stress. And this, what is this point now? This is the yield point now, where we have shown this Fy. So next now, this is now the idealized diagram. We are going to use this for the plastic analysis. Now showing here now the concept, let's we have simply supported beam and at the mid we have a pointed load which is P. So gradually we will start increasing the load till it reaches the ultimate load or the failure load or the limit load. So as the bending moment is increased at a particular section of a beam, there will be a linear variation of stress until the yield stress is reached in the outermost fiber. When there is no load, what will happen? There will be no stress along the cross section. But when we start gradually increasing the load, so even in the outermost fiber, even the stress will be less than Fy. It will be a straight line, but Fb, the stress, bending stress in the beam in the outermost fiber, it is going to be less than Fy. With further increasing the load, what will happen? The outermost stress will reach to the Fy. Now, that is the yield strength of the beam now. What will happen if we start increasing further load? Now the outermost layer stress, it will remain at Fy, but now adjacent to it, the layers, they will start reaching the Fy now. And slowly this process will go on till it reaches the neutral axis. Even at the neutral axis, then the stresses will be equal to Fy. So now from triangular shape of the bending stress distribution, it will be becoming a rectangular stress distribution now. At ultimate, what will happen? The stress distribution from the triangular, it will become a rectangular stress distribution. On one side, the full beam will be having rectangular stress distribution in compression, while on the other side it will be having in tension. Let's take a beam of rectangular cross section subjected to point load that is increasing from a value of P to PU ultimate. From P, any load P, it is going to PU, and this is the configuration. Now simply supported, having rectangular cross section, prismatic, and then P is applied at the mid span. Now, for a rectangular beam, the illustration of stress variation in the elastic range is shown in the figure below. So this is the cross section here, cross section of this beam, and this is the stress distribution, bending stress distribution. At neutral axis, you see it is 0, and when we start moving away from the neutral axis, this is Fy. This stress is increasing. Now, remember, Fp is less, so what will happen? This triangular distribution will become this way. Here, if you are looking at this cursor now, so it means this F will be less than Fy, but by increasing the load, what will happen? Now you will get the outermost now fibers at the yield stress now, which is Fy. So up to here, it is elastic behavior. Now, if we increase further load, what will happen? It will stay at Fy, but now the layers adjacent to it, now it will start at yielding now. We'll be showing it in the next slide. With further increased load, again yielding, and finally the yielding will reach to the neutral axis now. So this will become now a rectangular, similar here, it will become a rectangular stress distribution. So the yield moment of a cross section is defined as the moment that will just produce the yield stress in the outermost fiber of the section. So from here onwards, you should be clear about the yield moment. Why we will be discussing the yield moment, then we will be discussing the plastic moment, and when we find out the ratio between the plastic moment and the yield moment, that will become your shape factor now. So yield moment definition is what? It is coming from this state now. It is the moment capacity of this section which will just produce the yield stress in the outermost fibers of the section, outermost fiber of the section. Let's say partially the under layers, they are also under Fy now. So that will become now elastoplastic moment now, because partially it is elastic and partially it is plastic now. And now let's say the whole section is coming under this Fy, and this is also under Fy, then that is fully plastic section. That is known as fully plastic section. We'll be discussing this in a moment. Now, if the moment is increased beyond the elastic moment now, the outermost fibers will continue to have the same stress, but will yield, and the duty of providing the necessary additional resisting moment will fall on the fibers nearer to the neutral axis. Right, so it will start now propagation towards the neutral axis now. This process will continue with more and more parts of the beam cross sections stressed to the yield point until finally a fully plastic distribution is approached as shown on the next slide. So here now you see what is happening. This is the beam plastic hinge now, how it is going to form now. So this is now rectangular beam cross section. Here you see this is the stress distribution. The first yield is happening, the first yield at the outermost fibers. So it's purely a triangular stress distribution now. Only the outermost fiber are at the yield stress. After this, if we increase further the moment, what will happen now? Towards now the neutral axis, the layers will start reaching the status of Fy. So here you see here now up to here the layers, and up to here the layers they are reaching. With further increase now, this yield layers, further layers will get to the yield stress. Finally up to the neutral axis. You see here now it's rectangular and rectangular stress distribution. This is elastic cross section, but here it is elastoplastic and here it is fully plastic now. When the stress distribution has reached this stage, a plastic hinge is said to have formed because no additional movement can be resisted at this section. Now after this, if you further increase the moment, what will happen? It will start free rotation now. It cannot take any further movement now. This is the full capacity. Right, and now we will see if there are enough plastic hinges and elastic hinges, so it will start the mechanism. What mechanism? Failover mechanism. The structure is going to fail after that. We will discuss that one, but for now you should know when the plastic hinge is going to happen, when the section is fully plastic. And you should know now how we are getting from the under elastic to the elastic, from elastic to the elastoplastic, and from the elastoplastic to the fully plastic state. And you should be able to draw these stress distributions also. Now, any additional moment applied at this section will cause the beam to rotate with little increase in stress. The plastic moment now is the moment. Here is coming now. We already discussed the elastic moment. Now is coming the definition of the plastic moment. So the plastic moment is the moment that will produce fully plasticity in a member cross section and create a plastic hinge. After that, if you apply the moment, what will happen? It will start free rotation. Now here is now this whole section is now getting the whole section, this red, if you see, this whole has become now at the yielding point. And the whole section is, this is the area of yielding. So that is known as plastic hinge. Now plastic hinge is going to form here. At plastic hinge, what is the capacity now? At the plastic hinge, what is the capacity of the plastic hinge? If somebody is asking you, so that is the plastic moment. And what will happen when you increase further the moment now beyond the plastic moment? What will happen? It will become a hinge now. which is having the zero moment capacity, means it will start failing after that. And you see here at plastic hill, what we have? We have the failover load, which is PU, which is the ultimate load now. How this is formed now and how much this range we have. So let's discuss that now. Here now, at the top now, you see that simply supported beams. And we have just the yielding stress now in the outermost fibers here. You see the loading applied here. And P is just equal to Pi, which is the yielding load now. So the outermost fiber now, that they are at yield now. If we increase now this P greater than this yield load, what will happen? Under this now, these layers will also start yielding. You see here this H portion, yielding is now extending towards the neutral axis. So P is greater than the yield, but still it is less than the plastic or the ultimate load now. So this is the yielding zone. If you further increase the loads, and let's say it is reaching to the ultimate one, so now you see these two lines, they are meeting, the zones have joined now, and you see here now this is fully yielded, this portion is fully yielded, and now we have a plastic hinge. So here it will start free rotation now. You see the deflection, free rotation. And why free rotation? It was a stable structure, simply supported. But if we put an additional now hinge here, it will become now unstable structure because it will start free rotation now. Like a scissor, you can take it, will try to close now. So the structure is going to fail. So this is how from elastic we are going to the elastic plastic, and then from the elastic plastic we are going to the plastic behavior. And here we said that the plastic hinge has formed. This is the formation of the plastic hinge now. Now plastic hinge is zone of yield. Yeah. Hello?
सर ये जब यील्ड होगा, एक कंक्रीट यील्ड होगा हमारे पास, ये स्टील अपर फाइबर में तो हमारे पास कंक्रीट होता है, वो तो क्रश
नहीं, आप दोबारा बताएं आप प्लीज।
सर ये जो हमारे पास ये सेक्शन जो है ये कंक्रीट होगा या स्टील, मतलब नीचे वाले फाइबर में तो हमारे पास स्टील अगर हो तो वो तो सही है
यार। ये तो हम तो अब स्टील स्ट्रक्चर्स की बात कर रहे हैं ना। दिस इज अ स्टील बीम हैविंग द सेम प्रॉपर्टी इन द टॉप एंड बॉटम, right? So this the beam we are discussing right now, it is the steel beam now having the same properties in tension and compression. ठीक है, आप आरसीसी की तरफ चले गए तो आरसीसी में ऑलरेडी आपने डिस्कस किया हुआ है वो विटनी डायग्राम्स और वो सारी चीजें, बट दिस इज अ स्टील स्ट्रक्चर। ठीक हो गया?
ओके सर। अच्छा,
यहाँ पे क्या है? प्लास्टिक हिंज इज जोन ऑफ यील्डिंग एंड इट्स लेंथ इज इक्वल टू एलपी। तो इस एलपी, इस प्लास्टिक जोन, इसकी हम बात कर रहे हैं। यहाँ पे अगर आप देख लें, इट वाज द प्लास्टिक जोन नाउ, लेकिन इसमें अगर आप देख लें, वी आर ड्राइंग 3 सेक्शंस। ए सेक्शन, अगर ये वर्टिकल लाइन आप देख लें तो यहाँ पे सारा सेक्शन जो है ना, व्हाट इज हैपनिंग टू दिस, ऑल दिस सेक्शन, ऑल दिस क्रॉस सेक्शन इज यील्डिंग। बीबी में क्या है? इस पे अगर आप आ जाए तो इसमें पार्शियली इट इज यील्डिंग। टॉप और बॉटम में अगर आप देख लें, रेड पोर्शन जो इट इज यील्डिंग, बट द मिडल पोर्शन इज नॉट यील्डिंग। और सी पे अगर आप देख लें, सो ओनली द टॉप लेयर्स आर यील्डिंग, इन बिटवीन इट इज नॉट यील्डिंग। मतलब क्या है? ये देखिए आप एंड पे जो आपका सी सेक्शन है, इसी तरह इसी यहाँ पे भी है। आप इसका मिरर इमेज कर ले तो एम वाई, ये आपका यील्ड स्ट्रेंथ, और यील्ड स्ट्रेंथ हो गया सी पे। वाई यील्ड मोमेंट? बिकॉज ओनली द टॉप मोस्ट फाइबर्स आर यील्डिंग। मिडल पे अगर आप देख लें, पूरा सेक्शन आपका यील्ड कर रहा है, सो दिस इज द प्लास्टिक मोमेंट। और बीच में अगर आप देख लें, सो दैट इज इलास्टोप्लास्टिक। सम ऑफ द पोर्शन इज इन इलास्टिक and some of the portion is not in the elastic, so that is known as elastoplastic. So section AA, which is this middle one, it is completely plastic. Section BB, it is partially plastified. ये upper portion और lower portion जो है ना, इसका plastified हो गया है। और section CC is only plastified at the outermost layer. तो आउटर मोस्ट फाइबर पे यहाँ पे जहाँ पे यील्डिंग, उसको हम प्लास्टिफाइड कहते हैं कि यहाँ पे आपका प्लास्टिफिकेशन जो है ना वो शुरू हो चुका है. सो अब ये कितना होता है ये जोन लेंथ ऑफ दिस LP is most of the time it is L/3. L is the length of the beam. So plastic hinge ये तो हो गया ना is equal to LP. ये LP हो गया. ये definitions हमने के MYQ लिखा हुआ है, फिर MP के ऊपर उनके definitions भी हो गए कि middle range में क्या हो रहा है, इस H पे क्या हो रहा है, middle पे क्या हो रहा है. LP is equal to L/3. This can be proved. The moment capacity of real hinge is 0. अच्छा, real hinge जब हम लेते हैं, आपको याद पड़ रहा है जिसको हम सॉलिड डार्ट से शुरू करते, वो सर्कल से शुरू मतलब शो करते थे, उसकी कैपेसिटी कितनी थी? That was 0. Moment at that we took equal to 0. But moment capacity of the plastic hinge is MP. Remember, a plastic hinge की moment capacity कितनी होती है? That is maximum, which is MP. इससे ज़्यादा अगर आप moment लगाएंगे, then it is going to convert into the real hinge. इसके बाद fail हो जाएगा वो जगह और उसका क्या है? That will become real hinge. So after the formation of the plastic hinge, it can safely resist moment up to MP. ठीक है, प्लास्टिक हिंज तक आप क्या MP आप वो ले सकते हैं. इसके बाद जो है ना it is going to start free rotation like a real hinge. Now the effect of plastic hinge is assumed to be concentrated at one section for analysis purposes. Analysis purposes के लिए हम ये LP इतना नहीं लेते, एक ही पॉइंट पे जहाँ पे आपका मैक्सिमम बेंडिंग मोमेंट आ रहा है वहीं पे हम लेते हैं कि plastic hinge is going to occur at that location. However, it should be noted that this effect may extend for some distance along the beam. तो इसको आप spread भी कर सकते हैं. अब कहाँ पे आपका होगा मैक्सिमम मोमेंट? जो अब अगर मैं आपसे कहता हूँ कि मैक्सिमम मोमेंट अगर पॉइंटेड लोड लगा हुआ है आपका सिंपली सपोर्टेड बीम पे, तो कहाँ पे होगा मैक्सिमम मोमेंट? अंडर द पॉइंट लोड. तो जहाँ पे आप एंटिसिपेट कर रहे हैं मैक्सिमम मोमेंट, दैट इज द potential location for formation of the plastic hinge. Now the location where moment is maximum, possibly there will be a plastic hinge. This is the simple basic principle. Now the possible locations are below the point load हो गया, within the region of distributed load. अब आप देख लें distributed load है तो वहाँ पे आपको maximum moment की मतलब possibility हो सकती है. एंड एट रिजिड जॉइंट अगर आप फिक्स सपोर्ट पे देख लें तो अक्सर वहां पे आपका मैक्सिमम मूवमेंट आता है, तो वहां पे भी प्लास्टिक हिंज की पॉसिबिलिटी हो सकती है. अब आते हैं कि यील्ड मूवमेंट हम कैसे मालूम करते हैं. दिस इज कमिंग फ्रॉम योर बेसिक जो आपने पहले किया हुआ था. स्ट्रेस किस चीज के बराबर था? स्ट्रेस वाज इक्वल टू बेंडिंग स्ट्रेस की बात कर रहा हूँ. डायरेक्ट स्ट्रेस तो था आपका P डिवाइडेड बाय A, लेकिन बेंडिंग स्ट्रेस की जब हम बात करते हैं तो दैट वाज F इज इक्वल टू M डिवाइडेड बाय S, और M इज इक्वल टू F टाइम्स S नाउ. लेकिन यहाँ पे हम कौन सी स्ट्रेस की बात करते हैं? हम यील्ड स्ट्रेस की बात करते हैं, बिकॉज वी आर टॉकिंग अबाउट द यील्ड मोमेंट. So the yield moment My is equal to the yield stress times the elastic modulus, the elastic section modulus, which is S. वही है F is equal to M divided by S. इसको अगर आप reorganize कर लें तो क्या M is equal to F times S now. चूंकि yield की हम बात करते हैं तो हम क्या लेते हैं? It is Fy times this My is equal to Fy times S. Y is for the yield now. अब सेक्शन मॉडुलस हम कैसे मालूम करते हैं? इलास्टिक सेक्शन मॉडुलस दैट इज इक्वल टू I डिवाइडेड बाय C. अब I क्या था उसके लिए? रेक्टेंगुलर सेक्शन के लिए दैट वाज BH क्यूब डिवाइडेड बाय 12. C क्या था? H डिवाइडेड बाय 2. तो इसको अगर आप अब कर लें, इसको सिंप्लीफाई कर ले तो क्या होगा? दैट विल बिकम BH स्क्वायर डिवाइडेड बाय 6. ठीक है, या तो आप I मालूम कर ले, C मालूम कर ले, इसका रेशो मालूम कर ले, दैट इज बिकमिंग योर सेक्शन मॉडुलस. या क्या करते हैं, हम इसको सिंप्लीफाई कर लेते हैं तो BH स्क्वायर डिवाइडेड बाय 6. H इज द हाइट एंड B इज द विड्थ. यहाँ हाइट को हमने किस चीज से शो किया हुआ है? D से शो किया हुआ है. सो द इलास्टिक सेक्शन मॉडुलस इक्वल्स टू I डिवाइडेड बाय C. or BD square divided by 6, and for a rectangle, this is for rectangular section. तो rectangular section के लिए हम कैसे मालूम कर सकते हैं? My जिसको हम yield moment कहते हैं वो आपका Fy होगा। ग्रेड 40 स्टील हम कहते हैं, तो ग्रेड 40 स्टील मतलब क्या है कि उसका yield stress जो है ना 40 KSI है, that is 40 KSI, या yield strength क्या है, that is 40 KSI। 60 ग्रेड के लिए क्या होगा, 60 KSI होगा। तो Fy यहाँ पे आपका 60 के लिए, तो ये आपका 60 हो गया। अब बीम का विड्थ होगा, आपके पास उसका डेप्थ होगा, उसका स्क्वायर डिवाइड बाय 6 कर ले, इसको मल्टीप्लाई कर लें, that will give you the yield moment capacity of the section. The same value can be obtained by considering the resisting internal couple. यही इक्वेशन जिसको हम कहते हैं Fy times BD square divided by 6। तो ये आपके कहाँ से मालूम कर सकते हैं? By finding out the internal moment resisting capacity of the section. पहले हम क्या करते हैं, इंटरनल कपल हम एस्टेब्लिश कर लेते हैं। कपल को हम क्या करते हैं, डिस्टेंस बिटवीन द कपल, तो उसको अगर हम मल्टीप्लाई कर लें, दैट विल गिव यू द इंटरनल resisting capacity of the section. यहाँ पे शो किया हुआ है, look, this is a cross section having width B now, depth is D. This is the stress distribution diagram, and which one, where we are just getting the outermost fiber at the yield stress now, Fy and F1. अब यहाँ पे compressive force आप कैसे मालूम करेंगे? This is just the area of this upper triangle. तो यहाँ ऊपर आपका क्या है, ये C आ रहा है compressive force. It will be the area of this triangle. Area of this triangle क्या होगा? It will be half of Fy times D divided by 2. So ये हो गया half times Fy times D divided by 2 हो गया, और कितने width पे, width से आप multiply, it is actually the volume of this area. यहाँ तक जो है ये सारा compression में आ रहा है। So half times Fy times D by 2, या इसको आप इस तरह ले सकते हैं कि this is the average force now from 0 to Fy. So force times area, area कितना है इसका? Area is D by 2 times this B, D by 2 times B यहाँ पे आ गया। So force times the area, which is equal to, this is average stress actually, average stress times the area, which is equal to force. So we now end up with FYBD divided by 2. Similarly, from the lower triangle, you can find out the tensile force now. Again, it is stress times the area. The average stress, tensile stress, is half times Fy, and D by 2 times B. It is the area of this portion which is in tension. So again, FYD divided by 2. What will be now the moment resisting capacity of this couple? It will be force times this distance now. So force is FYDB divided by 2, which is written here, multiplied by the distance. So if you see here, again, we get this FYBD square divided by 6, where BD square divided by 6 is the section, elastic section modulus of this cross section. Yield moment now for a rectangular cross section, the yield moment will be equal to FYBD square divided by 6. Section modulus is the ratio of the moment of inertia to the distance from the neutral axis to the outermost fiber. Section modulus, you know, Fy, you know, to find out the product, and that gives you the yield moment capacity of the section. Plastic we need to discuss now. What is a plastic moment? So next we go to the plastic moment. Now the plastic moment MP is equal to the yield stress. Now again, if you see now, again we are yield stress. We are not going beyond the yield stress now, and it is times the plastic section modulus. What is the plastic section modulus? Now elastic we discussed, I divided by C now, but what is the plastic? So we'll discuss this now. The plastic section modulus equals to BD square divided by 4 now. In case of the rectangular section, it is BD square divided by 4 instead of BD square divided by 6 now. So you see now it's in a way it is more than the elastic section modulus. And MP will be equal to Fy times Z. So instead of Z, we are putting now the section modulus, this plastic section modulus value here. Now from here you can see that MP is greater than the My now. So you are now the shape factor, which is the ratio of the MP to the My, it is always greater, it is always going to be greater than the 1, than the unity. The same value can be obtained by considering the resisting internal couple. So again, the same concept we are going to use now. Here the stress distribution, now you see it is fully plastic. So we see each and every layer at Fy now. Now d by 2, so this is the location of the neutral axis. For the elastic and plastic now, the neutral axis will be same in case of the rectangular, but for the other sections, it is not going to be the same. Let's say it is unsymmetrical section. So elastic neutral axis and plastic neutral axis, they are going to be different. For the elastic, already you know how to find out, but for the plastic, how do you find out? We will discuss this. The resisting moment equals T or C times the lever arm between them as follows. So now here now, what is now the compressive force here in the top? It will be just the stress times the area. Stress throughout now, we are not taking the average now, throughout it is Fy. So it becomes Fy times D by 2 times B, D by 2 and times this B. So this whole section now multiplied by this B, it is now in compression. And similarly in tension, we have the same situation. Against force times, again force times the distance, that will give you the internal moment resisting capacity of the section, which is the plastic moment. So Fy D divided by 2 times B. It is the force now and times the distance between them. And now we can see that the plastic moment is equal to Fy BD square divided by 4. So this is Fy BD square divided by 4. Now coming to the shape factor now. So the ratio of the plastic moment to the yield moment now is called the shape factor. So shape factor, which is mu, is equal to MP divided by My. What is MP? Fy times Z now. What is Z? It is the plastic section modulus. And similarly My, so again it is Fy times S now. S is the elastic section modulus. Plastic section modulus, how we find out the Z, we will discuss. The shape factor equals 1.5 for rectangular section as to below, and varies from about 1.1 to 1.2 for standard rolled beam sections. What is the standard rolled beam section, which are made in the factories like W sections and all those HSS and those? You need to go to the ASIC that manual to see all those properties. So now shape factor is equal to MP divided by MYR. Now you can do it Z divided by SR. Also why? Because Fy and Fy, they are getting cancelled. So it's in a way, it's a ratio of the plastic section modulus to the elastic section modulus. So for rectangular section, it was BD square divided by 4. And it is BD square divided by 6, the section modulus for rectangular. The elastic section modulus, BD square, these will cancel, it will become 6 divided by 4. So 6 divided by 4 is equal to 1.5. So that is why sometimes it is asked that you now give me the ratio, or you give me the shape factor for a rectangular section. It is 1.5. How it is coming? It is coming from the ratios of the plastic to the elastic section modulus. Now here for the different shapes it is given. For the diamond section it is maximum. For the circular section it is 1.7. Plastic limit, as we said, it is 1.5. For this one, for the hollow section, it is 1.27, and for this I shape, it is 1.14. So for the diamond shape, it is maximum. These are the different shape factors. This SF, it is for the different shape factors, and you can prove them also just by finding out C and S values and finding out the ratios of these. Now, plastic neutral axis, you will need this to find out the Z value. So what is a plastic neutral axis now? The neutral axis for plastic condition is different than in counterpart for elastic condition. Unless the section is symmetrical, the neutral axis for the plastic condition will not be in the same location as for the elastic condition. So it's going to be different. The total internal compression must equal the total internal tension. In plastic analysis, the neutral axis is the equal area axis, right? This is that axis which is divided the cross section into equal areas. And how, let's see now how we find out. At all stages of loading, the compression force C induced by the applied moment must equal to the tensile force, right? In order to be in equilibrium, C compressive force must be equal to the tensile force, which is T. Or the plastic neutral axis must be that axis which equally divides the area into two separate parts. That is, C is equal to compression force, which will be equal to area of compression into the yield stress. Tensile force, which is equal to area of area and tension multiplied by the, and if we put them in equilibrium, so Fy is going to cancel with Fy, and it means that C will be equal to T, or here we can say area in compression will be equal to the area in tension, because the material Fy is going to be the same on tension and compression side. The plastic modulus Z is defined as the ratio of the plastic moment MP to the yield stress. Now this is the Z definition now, the plastic modulus. What was MP? MP was equal to Fy times Z now. So Z will become MP divided by Fy now. So the plastic moment modulus, the plastic modulus Z is defined as the ratio of the plastic moment MP to the yield stress Fy. This is coming from their basic definition. MP is equal to Fy times Z. It can also be defined as the first moment of area about the neutral axis, where the area above and below the neutral axis are equal. So this is the second definition. And how we can do it? If we go there now, look, Z, we said it is BD square. Z is equal to BD square divided by 4. So how it is coming now? Here, if we see area above and area below, this D by 2, they are the same now. So if we start the first moment of this area about the neutral axis, what will happen? It will become now BD by 2. It is the area of the upper one now. B times D divided by 2, which is written here, and times its first moment of area. So what will be now the moment of area? It will become D divided by 4 now. So BD divided by 2 and multiplied by D by 4, and similarly from here now we have, so if we multiply that by 2, it will become equal to BD square divided by 4. It is the first moment of area actually about the plastic neutral axis. So you can find out C by using this concept. Now, how we find it out? Let me see. It is 9:32 now. So let's, and we are in slide 41 now. So hopefully we go like 5-6 slides more, and then we will stop. And the remaining lecture we are going to finish tomorrow, inshallah. And tomorrow, what time we are meeting now? Sijad, if you are there, so you tell me.
Sir, 8 a.m.
8 a.m. tomorrow.
Yes, sir.
You are comfortable 8 o'clock, or even if you can come 7 o'clock, so I'm fine with 7 o'clock also.
Sir, 7 पता नहीं सर 7 तो मुश्किल है आई थिंक सर.
अच्छा ठीक है, so we meet then. The 8 o'clock we'll meet inshallah. Right, we'll be doing some problems. अब इसको हम कैसे मालूम करते हैं? So this unsymmetrical section is given. Now you study this carefully. टॉप पे जहां पे A1 लिखा हुआ है, ये A1 क्या है? अनशेडेड पोर्शन के लिए हमने लिखा हुआ है. ये आपका होगा लेट्स से कंप्रेशन में, और नीचे जो आपका शेडेड पोर्शन है लेट्स दैट इज इंटेंशन. ये दोनों एरियाज अब क्या है? मटेरियल प्रॉपर्टीज तो वैसे भी है कि ये कंप्रेशन और टेंशन में, तो ये दोनों क्या है? ये दीज शुड बी इक्वल टू ईच अदर. अब अगर ऊपर आप देख लें तो फ्लैंज का विड्थ कितना है? ये 50. अगर फर्ज करें ये सिमेट्रिकल होता तो फिर तो आप क्या करते? इसको आप सेंटर में आप रख लेते इसके मिड डेप्थ पे सिमेट्रिकली. लेकिन अब क्या है? सेक्शन आपका अनसिमेट्रिकल बन रहा है. तो अनसिमेट्रिकल के लिए हम क्या करते हैं? अगर ऊपर आप देख ले 15 इंचेस फ्लैंज का विड्थ है, नीचे क्या है? 8 इंचेस हो गया. अनसिमेट्रिकल हो. थिकनेस ठीक है 1 इंच, लेकिन टॉप जो है फ्लैंज दैट इज डिफरेंट फ्रॉम द लोअर वन. तो अब इसको क्या करना है? अबाउट द प्लास्टिक न्यूट्रल एक्सिस आपने इसको इक्वल एरियाज में डिवाइड करना. अब कैसे करेंगे? सो इट्स अ सिंपल मैथमेटिक्स. नाउ हम एक रेफरेंस पॉइंट ले लेते हैं. लेट्स से यहाँ से लेके यहाँ पे हम YUN इसको हम कहते हैं, और यही YUN न्यूट्रल एक्सिस तक अगर ये डिस्टेंस हम मालूम कर लेना तो फिर इसका हम क्या कर सकते हैं? इनके हम एरियाज भी मालूम कर सकते हैं कि कितना कंप्रेशन में आ रहा है, कितना टेंशन में आ रहा है, और उससे हम Z भी मालूम कर सकते हैं. तो पहले ये कर रहे हैं. अब Z के लिए क्या है? इट इज मस्ट दैट यू शुड बी नोइंग द न्यूट्रल एक्सिस, प्लास्टिक न्यूट्रल एक्सिस. अब प्लास्टिक न्यूट्रल एक्सिस हम कैसे मालूम करेंगे? अब कहते हैं कि लोकेट द प्लास्टिक न्यूट्रल एक्सिस एंड फाइंड आउट द प्लास्टिक मॉडुलस फॉर द फिगर शोन बिलो. The areas above and below the neutral axis must be equal for plastic analysis. ये है इसका basic. This is the basic statement. अब क्या करेंगे? आप इसको जब आप मालूम करेंगे, so you need a reference point, और वहीं से आप डिस्कस मालूम करेंगे. So quickly if you want to draw it, आप इसको ड्रा कर लें ताकि नेक्स्ट स्लाइड पे जाके हम इसको कर लें. चलेंगे इसमें. तो हम क्या करते हैं? दिस इज द बेसिक नाउ कि A1 मस्ट बी इक्वल टू A2. A1 ये ऊपर वाला पोर्शन है और A2 हम नीचे वाला पोर्शन है. तो ऊपर वाला पोर्शन A1 क्या होगा आपका? 15 टाइम्स 1 यहाँ से आ गया, और इसका ये नीचे वाला जो पोर्शन है इसका, दिस वर्टिकल रेक्टेंगल, इट इज नाउ 15 माइनस y. ये देखे ये पूरा था आपका 15, तो 15 माइनस YN, ये आपका ये रिमेनिंग हाइट हो जाएगा. तो 15 टाइम्स y, 15 माइनस YN एंड टाइम्स क्या होगा? 1. ये आपका इसका एरिया हो गया. ये दोनों रेक्टेंगुलर पोर्शंस हमने A1 के लिए इंक्लूड कर दी. एंड इट मस्ट बी इक्वल टू द लोअर पोर्शन. तो लोअर पोर्शन में देख लें ये डायमेंशंस तो आपके क्लियर है. ये फ्लैंज जो है 8 टाइम्स 1 हो गया, तो 8 टाइम्स 1 हो गया A2 के लिए, प्लस ये वर्टिकल रेक्टेंगुलर जो यहाँ पे आ रहा है टेंशन के लिए, दैट इज YN टाइम्स इसका थिकनेस कितना है? कहीं पे लिखा हुआ, या इट इज रिटन हियर, सो इट इज 1. तो ये ऊपर का हो गया. अब ये 1 अननोन है इसमें YN, तो ये डिस्टेंस बड़े आसानी से आप मालूम कर सकते हैं. तो कितना आ रहा है? YN इज इक्वल टू 11 इंचेस. ये डिस्टेंस आपका 11 इंचेस, तो ये कितना रह रहा है ऊपर बॉटम ऑफ द फ्लैंज तक? ये आपका 15 माइनस 11, तो ये 4 इंचेस आपका रह रहा है. अब प्लास्टिक हिंज अगर आपको कहते हैं कि ये एक्सिस कहाँ है, कहाँ पे, तो बॉटम से अगर आप नापते हैं इसको तो ये 12 इंचेस पे आ रहा है, 1 प्लस 11. और टॉप से अगर आप नापते हैं तो ये 17 माइनस 12, तो ये 5 इंच पे आ रहा है यहाँ से. अब Z कैसे मालूम करेंगे? इसका प्लास्टिक मॉडुलस अभी इसी सेक्शन पे आप आके इन्हीं एरियाज का आप फर्स्ट मोमेंट ऑफ एरिया मालूम करेंगे. That is the first moment of areas about the plastic is neutral axis. देखिए 8 times 1 लोअर से हम स्टार्ट लेते हैं, तो ये आपका हो गया 8 times 1, और ये डिस्टेंस कितना है, ये यहाँ से हाफ इंच निकल गया, 12 आ रहा था, तो 12 माइनस 0.5 तो 11.5, ये इसका मोमेंट आर्म हो गया, लोअर वाला फ्लैंज आपने कवर कर लिया, प्लस 11, ये वाई एन कितना था, अब ये वर्टिकल का हम लेते हैं, तो वर्टिकल हाइट हो गया, इसका एरिया हम मालूम करते हैं, तो ये 11 times 1 हो जाएगा एंड टाइम्स 5.5, तो 11 डिवाइडेड बाय 2 कितना आ रहा है, दिस इज 5.5, तो इसका मोमेंट आर्म हो गया। अब ऊपर वाले पोर्शन पे आ जाए, तो ऊपर वाले पोर्शन में पहले हम फ्लैंज ले लेते हैं, तो फ्लैंज कितना हो जाएगा, 15 times 1 ये एरिया हो गया, टाइम्स 4.5, अब देखते हैं कि 4.5 आ रहा है, बिल्कुल आ रहा है, ये 4 हो गया, और इसके सेंटर तक जाने के लिए 0.5 और आप ऐड करेंगे, तो ये इसका मोमेंट आर्म हो गया। अब ये वर्टिकल रेक्टेंगल के लिए हम करते हैं, तो ये डिस्टेंस आपका 4 times 1 एरिया हो गया एंड टाइम्स 2, तो ये हो गया एंड दिस 228, तो ये आपका प्लास्टिक मॉडुलस जी मालूम हो गया। एनी क्वेश्चन?
सर इसमें साइन चेंज नहीं होंगे सर जी?
No, it will be adding. Sign तब change होगा if you have a hollow section or something. ठीक है ना, टेंशन और कंप्रेशन में आप जाएंगे, it is making a couple now. ठीक है, they are going in the same clockwise or counter clockwise direction. तो इसमें आप माइनस, अगर माइनस करेंगे तो फिर तो आपका जीरो आएगा, ये आप किस तरह कह रहे हैं, सेम एरियाज और ये सारी चीजें ना, तो समटाइम फॉर द सिमेट्रिकल सेक्शन सिंपली इट विल बी कमिंग जीरो, देन you will be adding them. Okay, we are talking about the areas. Next, आप उसमें किस तरह मालूम करते हैं, इलास्टिक में जब आप जाते हैं इसी तरह आप करते हैं ना, एड अप करते हैं अबाउट द न्यूट्रल एक्सिस, सारी चीजें वहां पे जब शिफ्ट करते हैं आप, कुछ याद पड़ रहा है कि नहीं, BH क्यूब डिवाइडेड बाय 12 आप करते हैं, और फिर प्लस AD स्क्वायर, वो एरिया मल्टीप्लाइड बाय जब आप शिफ्ट थ्योरम आप यूज करते हैं ना, वो सारी चीजें, सो इट इज द सेम थिंग, और वहां पे भी आप ऐड करते हैं। अब यहाँ एग्जांपल नंबर 2 की हम बात करते हैं, इसमें कहते हैं कि डिटरमिन द पोजीशन ऑफ द न्यूट्रल एक्सिस। अब इसमें आप न्यूट्रल एक्सिस कैसे मालूम करते हैं, द प्लास्टिक सेक्शन मॉडुलस, फिर कहता है कि अबाउट द एक्स एक्सिस आप क्या करें, इसका जी मालूम कर लें, एंड द शेप फैक्टर फॉर द वेल्डेड सेक्शन, ये दो इन्होंने क्या है, रेक्टेंगुलर सेक्शंस एक दूसरे के साथ वेल्ड किए हुए, जो कि टी की शक्ल में आप देख रहे हैं। टॉप अगर आप देख लें तो 90 विड्थ है इसका फ्लैंज का, और डेप्थ है 10 मिलीमीटर, और वेब का अगर आप देख लें तो डेप्थ है 90 मिलीमीटर और इसका थिकनेस है 15 मिलीमीटर। अब इसका इलास्टिक सेक्शन मॉडुलस कैसे मालूम करेंगे, बड़ा आसान है, वो ऑलरेडी उन्होंने डायरेक्टली किया हुआ है, बिकॉज टिल नाउ इट वाज द प्रैक्टिस कि आप इलास्टिक मालूम करने सेक्शन, तो वो 34.99। कहाँ पे आपको इसकी जरूरत पड़ेगी, जब आप शेप फैक्टर पे जाएंगे ना, तो अब नई चीज में आप क्या करेंगे, आप जी मालूम करेंगे, एस ऑलरेडी आपके पास है, दोनों का रेशो मालूम करके आपका ये हो जाएगा। लेकिन अब इसमें हम देख लेते हैं कि हम कैसे, पहले हम प्लास्टिक न्यूट्रल एक्सिस कैसे मालूम कर रहे हैं, फिर आप जी कैसे मालूम कर रहे हैं। तो ये देखें यहाँ पे, अब अगर हम इज्यूम कर लेते हैं कि ये आपका ये जो ब्रोकन लाइन, आपको इसको फैंटम लाइन या जो भी कहते हैं, इसको देख लें, अबाव और बिलो अगर एरिया आप ऐड कर लेना तो आपका एक ही आपका आ जाता है, दिस इज दी areas above and below the neutral axis, they must be the same. अब अगर ऊपर आप देख लें तो दो, एक आपका हॉरिजॉन्टल रेक्टेंगल और ये रिमेनिंग वर्टिकल पोर्शन जो है ना, ये आपका आ जाता है। अब इसको हम कैसे करें, एरिया टोटल आपका AC1 प्लस AC2, ऊपर अगर आपका कंप्रेशन है ये ग्रीन वाला, तो नीचे ये ऑरेंज सा जो आपको नजर आ रहा है ये आपका टेंशन में, टोटल एरिया इन तमाम एरिया को जमा करके आ जाएगा। और कंप्रेसिव फोर्स C1 प्लस C2, C1 इज इन द फ्लैंज and C2 is in the web, these compressive forces. तो C1 प्लस C2 आपका टेंसाइल फोर्स के बराबर होना चाहिए। C1 किस चीज के बराबर होगा? AC1 जो कि इसका एरिया है यहाँ पे लिखा हुआ है टाइम्स Fy, और इसका क्या होगा? इसका AC2 जो कि यहाँ पे लिखा हुआ है टाइम्स Fy, और नीचे टेंशन का क्या होगा? AT एरिया इन टेंशन मल्टीप्लाइड बाय Fy हो जाएगा इसका। सो या Fy इज कॉमन नाउ, तो इसको हम कैंसिल आउट कर सकते हैं। सो AC1 प्लस AC2 मस्ट बी इक्वल टू AT। मतलब ये कि ये अगर आपका प्लास्टिक न्यूट्रल एक्सिस है तो इसका ऊपर वाला एरिया नीचे वाले एरिया के बराबर होना चाहिए। अब इसको कैसे हम मालूम करेंगे? तो यहाँ पे है आपका ए टोटल हमारा आ रहा है कि 15 टाइम्स 90, तो 15 टाइम्स 90 इस नीचे वाले पोर्शन से और 10 टाइम्स 90 ऊपर से, ये हो गया। अब हमारा क्या है कि ए टोटल आपका कंप्रेशन और टेंशन के बराबर होगा, लेकिन हमें ये भी पता है बेसिक प्रिंसिपल से कि एरिया कंप्रेशन एंड टेंशन बराबर होना चाहिए। तो हम क्या कर लेते हैं, अब हम कहते हैं कि area and compression will be equal to half of the total area, area and tension will be equal to half of the total area, तो 155। अब क्या है, नीचे में ये आप बड़े आसानी से, अब ऊपर से थोड़ा सा डिफिकल्ट होगा क्योंकि ये एरिया पूरा नहीं कर रहा है इसका हाफ, तो हम नीचे से मूव करते हैं। ऑलरेडी इसका विड्थ है आपके पास, एरिया एंड कंप्रेशन आपके पास आ गया, तो वाई प्लास्टिक हम कैसे मालूम करते हैं? दिस एरिया रिक्वायर्ड इन टेंशन डिवाइडेड बाय 15 विड्थ से हम कर लेते हैं, तो आपके पास इसका आपका डेप्थ आ जाता है विच इज 75 मिलीमीटर। ये देखें, ये यहाँ तक 75 हो गया, ऊपर से आप नाप सकते हैं इसको 10 प्लस, तो ये आपको 25 हो जाएगा। एनी क्वेश्चन है? कोई क्वेश्चन?
क्लियर सर, इट्स क्लियर।
अच्छा ठीक है, अच्छा ठीक हो गया। तो अब क्या करते हैं, अब यहाँ पे हम जाते हैं, ये देखिए आपका हो गया, ये इसमें थोड़ी सी गलती है, इसको आप ठीक करेंगे। ये नीचे जो जी हम मालूम कर रहे हैं, फर्स्ट मोमेंट ऑफ एरिया अबाउट प्लास्टिक। अब फर्स्ट मोमेंट ऑफ एरिया आप लेंगे तो 90 टाइम 10 हम ऊपर वाले से स्टार्ट ले रहे हैं, 90 टाइम्स 10 इसका एरिया हो गया मल्टीप्लाइड बाय 25। तो 25 तो नहीं आ रहा ना, क्योंकि ये क्या था 75, तो आपके पास कितना रहता है यहाँ पे? ये 15 रहता है यहाँ पे, इसके बॉटम तक, फ्लेंज के बॉटम तक। इसके सेंटर तक जाने के लिए आप 15 के साथ आप 5 जमा करेंगे, तो मतलब ये कि ये 25 जो लिखा हुआ है ये गलत है, ये आप क्या करेंगे? आप इसको 20 करेंगे, ठीक है। सो दिस विल बिकम 90 मल्टीप्लाइड बाय 10 मल्टीप्लाइड बाय 25, तो ऊपर वाले एरिया का आपका फर्स्ट मोमेंट ऑफ एरिया हो गया। फिर आ जाते हैं ये छोटा सा पीस जो है, तो ये कितना है? इसका विड्थ 15 और इसका डेप्थ भी 15 है, और इसका सेंट्रॉइड क्या होगा? इसका सेंट्रॉइड यहाँ के 15 डिवाइड बाय 2 जो कि 7.5 बनते हैं, तो इसका भी हो गया। प्लस अब ये नीचे वाला पोर्शन जो टेंशन में आ रहा है, इसको आप करेंगे तो फर्स्ट इसका एरिया मालूम कर लें, तो इसका 90 मल्टीप्लाइड बाय 15 हो गया, नॉट 90, दिस वन फ्रॉम हियर हम कर रहे हैं टेंशन में, तो 75 टाइम्स 15 हो गया, मल्टीप्लाइड बाय इसका मोमेंट क्या होगा? 75 डिवाइड बाय 2 जो कि 37। सो इसको आप कर लें। सो दिस इज द नंबर वी हैव। सिर्फ यहाँ पे थोड़ी सी गलती है, वो आप कर लें, क्योंकि हम मोमेंट ऑफ एरियाज लेते हैं, तो एरिया के सेंट्रॉइड तक लेके आप न्यूट्रल एक्सिस तक आप डिस्टेंस नापेंगे। अब जी हो गया, एस ऑलरेडी है आपके पास, तो ये देखिए इसका आप जब आप रेशो मालूम करेंगे तो ये इस शेप का अगर अब आप देखें इसका शेप फैक्टर कितना बन रहा है, दिस इज बिकमिंग 1.9। जी भी है आपके पास और एस भी 1.9। Now, fundamental conditions for plastic analysis. So already we are in now this slide 48 now. So I think it's a good point to stop now here. And the rest of the slides, which are like 54 slides remaining, so we'll cover them tomorrow. But till now, you should be clear what is the elastic section modulus, what is the plastic section modulus, what is the elastic movement, what is the plastic movement, what is the elastoplastic, all these things and how these things are going. Now, we will discuss the fundamental condition for plastic analysis, but that is going to be tomorrow. Now you tell me how many students, let me check if Faisal is there. Faisal, are you there? Mr. Faisal? Okay, now those who have YY exam today, they can stay and rest, can leave the this session now.